So today we are going to learn a topic called solid state control of drives. But before going to that, we need to know a very basic concept of SCR, that is silicon control rectifier, or a very general statement called because thyristors. Okay, so the main focus of today's lecture will be to know the working of SCR, what will be the objectives, outcomes that we will see, and what is the final question of the day. So, the objective of this session is to learn use of thyristor to control a drive. That means, if I say that I want to design a drive, how are you going to place the thyristors like SCRs or IGBTs? Okay. So, to control the speed of drive, this is the objective. But in this, the objective of use, that is how a thyristor can be used to control a drive, and the outcome is, so by knowing the thyristor, you can draw the output waveforms at the rectifier source, so that you can see that how I fire the thyristor and how will be the output at the output side of my drive. Okay. So, before going to start with it, let us first introduce the topic called solid state. The solid state, that means the current flowing through that is in solid form. So, what is the solid form current? It is in diamond form, in graphite, in iodine or sodium chloride. And what about non-solid state then? Non-solid state, that means cathode ray tube. In that the current is not in the solid form. So, what are the advantages then? The advantage of solid state is, the first one is efficiency, as they are very easy to control and there is less power loss. So, they are efficient to operate. Then lifetime, as there are no moving parts, so the lifetime of this devices is very high. Then what is a smooth control? Smooth control, that means whenever I can change the angle of firing, as we will see later, that is how SCR is fired, but before that, the way I fire the SCR, the smoothness of the output voltage will be gained. So, I can use some regulator and I can change the angle smoothly. Like there won't be any jerks when I change the speed using a SCR firing. Then I do have the thing like it's cost effective. So, the cost of all the semiconductor devices or solid state devices is comparatively very less than that of the non-solid state devices. Also, they are very lightweight and also they are small in size, not like that of CRTs and oscilloscopes. So, what are the types of solid state devices? There is an SCR, there is a DIAC and TROAC. So, SCR is unidirectional and TROAC is a bidirectional semiconductor device. We mostly go for SCRs in drives. So, the symbol for silicon control rectifier is, this is an anode, this is a cathode and there is a gate. In real time, we have a thyristor looking like this. Okay. Now, let us talk few points, very important characteristics of a SCR: holding current, latching current, forward and reverse blocking voltage, forward and reverse breakdown voltage. So, in this what happens? The SCR is made up of P and PN junctions. Okay. So, these are the 4 layers. Now, I get 3 junctions. First one is J1, second one is J2 and J3, and this is gate, anode and cathode. Now, how actually it conducts? So, first of all, there are 3 conduction modes of my SCR. The first one is reverse blocking mode, then the other one is forward blocking mode, and then the other one is a forward conduction mode. So, what is reverse blocking mode? In reverse blocking mode, what happens? We give negative voltage to my anode and positive voltage to cathode. So, the current will start flowing from anode to cathode, but what will happen? Basically, for conduction of the SCR, we need to provide positive voltage at anode. That is, VA should be greater than that of VK. It is the voltage difference should be VA minus VK should be greater than 0, but in this case it will be opposite. So, what will happen? When I apply some negative voltage at the anode point, the reverse current will start to flow. Okay. There will be this J1 and J3 will be not conduction mode and J2 will be in forward conduction mode. So, the moment like this, the situation is C like this one. So, I started increasing the reverse voltage, that is negative voltage. What will happen? It will try to block the voltage. There won't be any very high increase in the current, but I am trying to increase the voltage. So, at a particular point the voltage will be at its maximum, and that voltage is called breakdown voltage, reverse breakdown voltage, as we are going to reverse the use of SCR. So, since we have given negative voltage to the anode point, so what will happen, this voltage will go on increasing, increasing. After a certain limit, it will make the SCR go into breakdown, that is, it will be suddenly make the current, reverse current start to flow. This point is called as avalanche breakdown, that is, when very high reverse current will start to flow from that point, which is harmful, because there is always a limit. Here there is a limit, that is, after this voltage we should not increase, because what will happen, this may increase the temperature of my SCR and SCR may burn out. This is called as reverse blocking mode. That means, in this I will be having some reverse voltage as well as I will be having some reverse current. So, and this current will be mostly a leakage current. So, this what is called as a leakage current. Whenever I am applying some anode voltage in the negative, with a negative magnitude, then there will be some leakage current and it will be very less in the magnitude. Let us talk about the forward blocking mode. Now, what is, and in this case very important point is, I am just applying the voltage to anode and cathode, I am keeping this gate open. So, this scenario is affecting. Now, let us discuss what is the forward blocking mode. Now, in forward blocking mode, what will happen, I have provided positive voltage at anode and negative voltage at cathode, but I have not provided any voltage or any source at gate terminal, that is, gate is still open. What will happen then? The current will start on increasing, the voltage will also start on increasing, and it will reach at a point at which the breakdown will again occur, but that will be a forward breakdown voltage. That means, in this case the J1 and J3 will be forward bias. Now, this junctions J1 and J3 will be forward bias, but J2 will be reverse bias. So, what will happen? The current will start flowing from here to here, and at a particular point this junction will be breakdown, it will be open, it will start conducting, and that voltage is called as breakdown voltage or the knee voltage. And as soon as that situation occurs, the current starts increasing tremendously and my SCR starts in conduction mode. This is how it is going to operate in forward blocking mode. Gate is still open. Now, let us discuss two important topics in this mode. One is the holding current and the other one is the latching current. Now, what do you call by holding current and a latching current? So, the latching current is the current at anode, the current at anode, which is a minimum current which keeps the SCR on. Okay. So, the latching current is the current at which, or it is a minimum current at which the SCR will remain on. Then let us talk about what is the holding current. Again, holding current is the same. Holding current is the minimum current below which the SCR goes into off state. Holding current is the minimum current below which the SCR goes in its off stage. So, always the latching current should be greater than that of the holding current. This is a holding current, and then I do have a latching current at this point also. So, it is somewhere here. Okay. Now, let us discuss, we have discussed this breakdown voltage, blocking voltage, latching current, holding current. Let us discuss conduction mode. Now, how it is going to conduct? Now, see, this was the very high voltage required to make the SCR conduct without gate voltage. Now, what happens if I apply some gate current? So, this is a gate. Okay, so gate is triggered. So, there is no need of going into this direction. It is just directly very less voltage is required and the SCR goes on in conduction mode when I apply gate. Now, let us go ahead on how it actually works in an application. See, this is a waveform. This is an AC waveform. This is applied anode cathode voltage. Okay, so voltage is increasing now. This is what is called firing angle, that is at which my SCR is fired, and this is what is the remaining is called conduction angle. that is 180 degree is the total fan. Then gate pulse, that is 45 degree is the firing angle of my SCR. So, when the SCR is fired at 45 degree angle, the SCR will go into conduction mode like this one. The shaded part is called as the conduction mode, and whenever the negative waveform starts, it goes into off state. It is called natural commutation. Okay. So, naturally it goes into off state. Okay. Then now let us have an example, like I have a lamp load, I have a AC voltage, I have a SCR, and I am giving a gate pulse. So, this one is the normal, that is full conduction theta 1, okay, and this is a gate pulse. If I give the gate pulse like this, see theta 2 is the conduction angle. As soon as my gate trigger pulse, the gate trigger pulse changes, the conduction changes. Yes. So, when this is the gate trigger pulse, the conduction was full. When the gate trigger pulse came here, the conduction became changed. When it was later given, it was again changed. Okay. So, by this I can, as soon as I vary the gate trigger pulse and the angle of gate pulse, the output voltage will also change. Okay. So, we are at the end of our today's topic. We will just summarize what is thyristor then. They are semiconductor devices that can operate in switching mode. Yes, we have seen that is forward blocking mode, forward reverse blocking mode and conduction mode. And in this I need to switch. How I am going to switch? By applying the voltages. Now, thyristors are current operated devices. It is very important, they are current operated devices. A small gate current controls a large anode current. A very small gate current is applied as we have seen here. So, it is very small in magnitude. So, I can access, that is I can, based on this gate current, very small gate current also can make the anode or the thyristor to come into conduction. Conducts current only when forward bias and triggering current applied to the gate. The thyristor acts like a rectifying diode. Yes, it is very correct, because rectification, that means I want to get DC from AC, or I want to get fluctuating DC. I want to, that is pulsating DC, not fluctuating, the pulsating DC. And by using SCR, as we have seen here, the output waveform will be like this. Yes, omit this one. So, it will be like this, it will be like this, it will be like this. And if I again connect another SCR, what will happen? It will be like this. So, I will get some kind of this. I hope you have seen a full wave rectifier. This is for half wave rectifier. Then anode current must be greater than the holding current to maintain conduction. Okay, that is done. And once triggered on, it will be latched on conducting when gate current is no longer applied, providing anode current is above latching current. That means latching current is greater than the holding current. Okay, so these are the references from where I have taken this. And the question of the day is firing angle at which the thyristor can conduct for 50%. So, I want you all to know what is the angle at which the thyristor can conduct at 50%. Okay, so thank you for watching.